Hi, I'm Elizabeth Mountz, and I will be presenting my final project on generating depth maps from polarization cubes. Shape from polarization is based on the idea that the polarized elements of a partially polarized reflected light ray seen by a light sensor are a function of the surface normal relative to the light sensor. Therefore, polarization cues for 3D reconstruction can be collected by simply rotating a polarizing filter in front of a camera and recording the resulting changes in pixel intensity. The normal of a surface can be defined with the azimuth and zenith of the surface normal relative to the light sensor. These angles can be detected by measuring the relative RGB pixel intensities with a rotating polarizing filter. I captured 12 RGB images with the polarization filter held in front of the lens, rotated at increments of pi/6. The RealSense camera captures both point cloud depth maps and an RGB image, as well as the metadata for the camera intrinsic calibration to align these images. The point cloud can therefore be converted to a normal map and used to optimize the normal map from the polarization cues. I used a point source, e.g. a lamp, placed slightly in front of the object to illuminate the scene. The controlled lighting ensured that the RealSense only detected reflected light off the object, which had the appropriate polarization cues. Two critical limitations for the object were low-frequency surface changes and diffuse reflection. High-frequency surface changes are not captured well by the coarse point cloud generated by the RealSense, and therefore cannot contribute reliable azimuth ambiguity correction. Specular reflections create a different relationship between the relative intensity of the RGB pixels and the zenith angle and detract from the reliability of the methods used in this paper. The normal of a surface can be defined with the azimuth and zenith of the surface normal relative to the light sensor. I solved for azimuth, represented with phi, algebraically and found the average azimuth of the 12 images at each pixel. The azimuth angle can be solved for with the following equation and averaged over all pixels. I solved for the zenith, represented by theta, at each pixel and found the average for each pixel across the images. The degree of polarization, rho, can be solved for at each pixel as a measure of the amplitude and offset of the cosine function described in the azimuth equation. The degree of polarization is then related to the zenith of the normal with the equation shown. Rho diffusion specifies that the polarization cues are based on diffuse reflection from the object. N is the refractive index of the object. I estimated the refractive index to be about 1.5 for plastics and optimized it based on iterations of the pipeline. Since zenith could not be solved for algebraically, I used NumPy fsolve to find the zeros of the function at each pixel. I solved for the components of the normal using the zenith and azimuth calculations as follows. The results are extremely noisy. This is partially due to inherent noisiness in shape from polarization, as well as from uncorrected azimuth ambiguity. Here we see the ball object seen on the left and the three channels of the normal map represented as RGB channels in an image on the right. The polarization cues have azimuth ambiguity since the azimuths of 0 to pi and pi to 2 pi would yield the same degree of polarization. To correct the azimuth direction, I also needed a ground truth depth map of the object. RealSense camera generates a point cloud from which normals can be estimated and projected into the RealSense RGB image space using the intrinsic calibration of the camera. Shown are results from the ball object. The normal map from the RealSense point cloud are displayed on the left, with the three normal channels displayed as RGB channels, and each point projected to the image plane. On the right, these normals are overlaid onto the RGB image captured by the RealSense. Here we see the merged normal maps for the Kong toy object. It's a dog toy. The top left is the normal map from polarization cues. The top right is the normal map from the RealSense point cloud, and the bottom is the overlaid aligned normal maps. To correct for azimuth ambiguity, I use an optimization function between the normal maps from depth and polarization cues. The optimization function, with A as the coefficient of the polar normal, can be represented as follows, where A optimization is binary and gamma controls the smoothness of the optimization solution. Since the optimization operation is binary, I used a graph cut method. The corrected polarization normal map is much less noisy than the uncorrected normal map. So here's results. I ran the depth from polarization cues pipeline on 3 different objects, all of which met the constraints of low frequency surface variation and diffuse reflections. And all of the examples, raw polarization cues are sufficient to generate a noisy, high resolution depth map. All the examples demonstrate significant improvement in signal to noise ratio after azimuth ambiguity correction using the depth map from the RealSense. Here's the shape for polarization results for the ball object. Top left is the raw polarization normals visualized as RGB channels, and top right is a Franco integrated surface plot. The bottom row is the corrected polarization normals after graph cut optimization, and the resulting Franco integrated surface plot. These are the same images for the Kong toy example. The top left is the raw polarization normals visualized as RGB channels. Top right is a Franco integration surface plot. Bottom row is the corrected polarization normals after graph cut optimization. And finally, we have an example with a slipper. Thank you so much. And here are my references.